In this video, I'm just going to talk a little bit about how to calculate the rate of decay of radioactive nuclides. The rate of decay is the change in the number of radioactive nuclides in a sample per unit of time. So here we're looking at more of the kinetics behind the radioactive decay process, more of the kinetics behind the nuclear reaction. How fast does that nucleus decompose? Radioactive decay follows first-order kinetics. And since you may not remember all of the integrated rate laws for first-order kinetics, the integrated rate law is given here. It's the natural log of n over NO. I think when we did kinetics, we labeled that as A instead. And so that n and then the n naught actually is the amount of the substance that is decomposing. The n with the little, zero, or the n naught is the original amount of that whatever that nucleus is. That can be in concentration, it can be in grams, it can be in milligrams. It doesn't matter because as that is a ratio, as long as the units are the same, that will cancel out. The regular n is indicating the amount that remains at time t. So if you start with 1 and you go down to 0.5, it would be 0.5 over 1 as that ratio. And then the natural log of that ratio is taken and set equal to the negative k, the rate constant, times t, the time. The time can be in any units as well, seconds, days, hours, weeks. It doesn't matter. That will dictate what the units on the rate constant are. Remember, the rate constant is different for every reaction and is dependent on temperature as well. The half-life is the time it takes for a substance to decay by half. So in my original example, if you're going from 1 to 0.5, that's decaying directly by half. The time that takes is called the half-life. Again, radioactive decay follows first-order kinetics, and that gives us a half-life equation as the half-life being equal to the natural log of 2 over k. A couple of examples here. It takes 8 minutes for a 1 gram sample of francium-210 to decay to 0.118 grams. So it's going from 1 gram to 0.118. What's the half-life of francium? Well, we can first find out, in order to know the half-life, we need to know the k. And the time here and the amounts here are enough information for us to solve for k. So we can take the natural log of the 0.118, the amount that remains, over the original amount, over 1 gram, set that equal to negative k times the time it took in order to decay to those quantities, 8 minutes. When you solve that, we take the natural log of 0.118 over 1 and then divide by 8 minutes, change the sign, you get a k that is equal to 0.27 inverse minutes. Again, it's inverse minutes because the time here was in minutes. If this were in seconds instead, k would be in inverse seconds. We can then use that k and set it up to use the half-life equation, take the natural log of 2 over the k to solve for the half-life, which would then be 2.6 minutes. In another example, we can do the opposite. What happens if we know the half-life, but we don't know the time it took, for example? In this one, it says how much time is required for a 6.25 milligram sample of chromium-51 to decay to 0.75 milligrams, if it has a half-life of 27.8 days. The half-life allows us to calculate the rate constant. The rate constant here would be equal to 0.0249, again, inverse days, because the time is in terms of days. We can then use that k and the quantities in the problem, the 0.75 milligrams over 6.25 milligrams originally, and solve for the time it took in order to decay to those quantities, which is 85.2 days. Problems like this obviously would require the use of a calculator. These would not be examples of multiple choice questions. These would be examples of calculation questions.